Hi chemists, we're going to talk in this video about the properties of alkanes. Yellow syllabus dot point here on the left. Explain the properties within and between homologous series of alkenes with reference to the intermolecular and intramolecular bonding present. I'm going to stick to alkanes though. So, got a nice picture of one here. Look at its structure with that 109.5 degrees tetrahedral geometry around each one. So we need to talk about the polarity of alkanes. Carbon-carbon bonds are not polar. Of course, I mean, each of them have an equal pull on the electrons, so they're going to share the electrons evenly. Carbon-hydrogen bonds are also nonpolar because they share their electron density fairly evenly too. Not as evenly as carbon-carbon, but not significant difference, enough to call it polar. So alkanes, if they just contain carbon to carbon and carbon-hydrogen bonds, which is the definition of an alkane, they're nonpolar molecules because they don't contain any polar bonds. Okay? So let's start to talk about the intermolecular forces between two alkanes then. Since the hydrocarbons are not polar, they can't have dipole-dipole interactions, and therefore not the stronger version, which is called hydrogen bonding. And there's no ions there, so there's no ion dipole and all that kind of stuff. All that, the only intermolecular attraction between two hydrocarbons is dispersion forces. So those temporarily induced dipoles, where when the molecules move close to each other, the electron distribution is kind of disturbed, and you get temporary little positives, delta positives, partial positives, and little partial negatives, and that's enough to attract some molecules together. Only very weak though. Okay, but the thing is, over a short distance it's very weak, but over a longer distance, when these molecules can get closer together, there's a stronger force because there's more kind of overlap or more closeness between them. So longer molecules, should be more specific, longer alkanes have larger intermolecular dispersion forces between them, holding them together, because the two molecules can move close to each other over a kind of a longer surface area. So if we're talking about octane and octadecane, they have different properties even though they've got the same intermolecular force there. And these physical properties, like melting and boiling point, change. So hydrocarbons have a relatively low melting points and boiling points because they only stick together with dispersion forces, which is the weakest intermolecular forces. But there is a variety in there though. Okay? And as I was just talking about, as the size of the molecule increases, the temporary dipoles increase, and therefore the strength of the dispersion forces increase. So larger hydrocarbons have higher melting points and boiling points than smaller hydrocarbons. Another thing that can affect the melting point and boiling point, because it affects the intermolecular forces, those dispersion forces, is the shape of the hydrocarbon. Okay? And we can talk about straight chain molecules will line up really well, whereas branch molecules can't line up very well at all. Okay? So when you have straight chain hydrocarbons, they can move close to each other, so that dispersion force, they're closer, it's stronger. When you have two branch molecules, the branches get in the way. Think about, actually, not a good thing to do, but think about ripping two branches off a tree and trying to push them close together. You're going to have a lot of trouble because all the little branches off those branches are pushing away from each other. That's what happens with these molecules, yeah? Those backbones can't get close to each other, so the dispersion force between two branched molecules is much smaller than those on a non-branched one, where they can get close together. Another property that we need to consider is electrical conductivity. Now, electrical conductivity is all about charges and movement. So we really haven't got that because we don't have any dipole effect here, and we don't have any ions, and so therefore electrical conductivity is very low to negligible for these. Solubility we need to consider too. So alkanes are insoluble in water. Now you may learn this because like dissolves like, which is an okay year 11 explanation, but let's delve a bit deeper here, okay? So I've talked about solubility before, and I talk about the three possible interactions between two different types of molecules. So here we're talking about hydrocarbons and water. So we need to consider three possible interactions. When we're talking about water and water, the two molecules attract each other with dispersion forces, dipole-dipole attraction, and dipole-dipole attraction that's so strong it fits hydrogen bonding criteria. So the strength of that attraction between water and water is strong. Okay, when you've got hydrocarbon and a hydrocarbon, we've talked about this, it's just dispersion forces between them. So it's very weak, this interaction. And between hydrocarbon and water, you've only got dispersion forces too, which are very weak. So when you've got water and hydrocarbons all mixed up together, what ends up happening is we've got three possible interactions, and one of them's stronger, much stronger than the others. So what ends up happening is all the water molecules just stick together. They don't really associate much with the hydrocarbons because it's only very weakly attracted to them, but it's strongly attracted to other water. So what you're going to have is your hydrocarbons, depending on the density, forming a different layer in the water. So we often talk about oil floating on water because it has a lower density of water. This is the reason why. Water just wants to stick with water. It doesn't want to stick with those non-polar molecules. Okay, let's swap up the solvent though. Let's talk about a non-polar solvent as opposed to water. Something like petrol. So, here we've got a hydrocarbon and a hydrocarbon. Dispersion forces is very weak. Okay, very weak interaction. Now we're talking about a non-polar molecule, the solvent, with another particle of the solvent will also only have dispersion forces because we've chosen a non-polar solvent. So that's also a weak attraction. Now between a hydrocarbon and a non-polar molecule, there's also only dispersion forces, which are very weak. So you can see all three possible interactions are about the same strength. So when you cause a mixture of this, one part's not attracted to the other any more than the rest of them. So they can intermingle really well and they form a homogeneous mixture or a solution. So that is why hydrocarbons are soluble in non-polar solvents, but why they're not soluble in water. Okay, now we've got an investigation to do. I'll leave it up to you guys to do. It's about conducting an investigation to compare the properties, I need to fix that up, of organic chemical compounds within a homologous series. I chose the alkanes, and we're going to do graph there, melting points and boiling points, without the figures for pentane, and we're going to see how linear it is and predict those melting and boiling points of pentane. Okay, I'll leave it up to you guys, but I think that's pretty much the end of the chapter. We've got an hydrolo, another hydrolo, the review questions, and the last things that we should know. Check those off, okay? You should know, you should be able to. Okay, thanks for listening. That's the last hydrocarbons video. Alright, catch you next time.